I'm going to break this lecture up into two parts. This first part is going to be detailing the stress state from torsion, kind of like stresses on an inclined plane that we've done for tension problems. We're going to do something similar for torsion. And then the second part will be a separate video on torsion of systems that will get us ready to talk about statically indeterminate bars and torsion. But before we get into the stress state from torsion, let's just review a little bit about what we learned from last time about the formula for stress for a bar and torsion. So I'm going to draw my bar as a free body diagram. And remember, in our class we're restricting ourselves to looking at circular cross sections. It could be a solid bar or it could be a hollow bar. But in our class, only circular cross sections. And so if we have this torque arrow going this way and this torque going this way, and if we draw a square on our block, on our bar, something called a stress element or a stress block, then we can indicate the shearing stress arrows that act on that little square. Shearing stress arrows come down this way. They go in the same direction as the torque does on that side, and on the other side, on the left side, the shearing stress arrows will go up this way because the torque is going up that way on the left side of the bar. Now we know from long ago at the beginning of the semester that shearing stresses always work as a set of shearing stresses. You don't just have two components, but you have a full set. And to keep this object in equilibrium, I would need an additional shearing stress on the top and an additional shearing stress on the bottom, where all these arrows point towards these corners. Let me draw this block out here a little bit bigger so that we can see this a little more clearly. We have all these shearing stress arrows, and they all have the same value of the torque. And if we're on the outside radius of the bar, the way that we would calculate that shearing stress would be the torque times the outside radius, or the diameter over 2, divided by the polar moment of inertia. In general, that formula is the shearing stress is the torque times the distance from the center of the bar to a point on the cross section divided by the polar moment of inertia, and that gives us what's known as a linear stress distribution. There's my circular cross section in the center of it. As I go out any radial line, if I apply a torque that goes this way on that object, then the shearing stress is very linearly with the distance from the center of the bar. That's what this equation says. This distance this way is the distance rho, and it's rho to the first power, so that's why it's a linear variation. Of course, if it's a hollow bar, it still varies linearly, but you only get the stress where you have material. Quite often on an exam, I will ask students to sketch the stress distribution for a bar in torsion, and this is what I want it to look like. Only have stresses where there is material. Don't overhang this stress distribution out here where we don't have any material. Alright, so what we want to do in this lecture is we want to start to take a look at stresses on an inclined plane from this stress state in torsion. Just like bars and tension, we are interested in stresses on an inclined plane. If you go back and look at the lecture for stresses on an inclined plane for bar and tension, we did a couple things. We took and we cut the bar at an angle, and we calculated the area of the inclined plane, and then we calculated the stresses on the inclined plane from the normal and the shearing force that act on that inclined plane. And we got some formulas for that. The approach that we're going to take here is similar, but there's a subtle difference. Here we already know what the stress is. It's a shearing stress tau that I have from this formula. We're going to convert stresses into forces and then apply equilibrium of forces. So let's get set up. In order to do this, we're going to take and use the same notation that our book does. We're going to cut this at some angle. They call the angle off the vertical the angle theta, and I'm going to redraw my block, that angled section of that block over here. And acting on that is the shearing stress that goes vertically over here, the shearing stress that goes over here, and I don't know what they are yet. They depend on the angle theta, but I'm going to have some normal stress and some shearing stress that act on the inclined plane that I'll call sigma n and tau nt in the n and in the t directions. What we want to do is we want to find sigma n and tau nt in terms of tau that I can calculate from the torque and the cross-section dimensions. If you might look at this, you might be tempted to write down summation of stresses equal to 0. Well, that's not something we can do. We don't do summation of stresses equal to 0. We have to do something called the summation of forces equal to 0 for equilibrium. What we need to do then is we need to convert these stresses into forces by multiplying them by the areas on which they act. To get a better picture of the area on which these stresses are acting, let's imagine taking this wedge and drawing it in 3D. A small thickness will take into the bar. So I'm going to draw this like a wedge. Let's see, let me use the red color to emphasize the sides. There's my blue line again. This is the angle theta from the picture. And in 3D it kind of looks like this. And I'll just dash in these hidden lines back here. Now I need some dimensions. I'm going to use this thickness dimension called T, and it's going to be a really tiny thickness, so small that the stresses don't change even though there's a linear variation. It's just a really tiny thickness. We'll see that it drops out of our equations in a little bit. And I'm going to call that slant length L. And so this blue area, the area of the inclined plane, is L times T. I do have some other areas I need to deal with. So that's the area that sigma n and tau nt act on. But there's another area back here. It's thickness T, but it has this side length over here. I'll call this side 1. And there's this side length over here. I'll call that S2. I can find out how S1 and S2 are related to the angle and this L dimension by just a little bit of geometry, a little bit of trig. If I take the cosine of the angle theta, that is going to be equal to the distance S1 divided by L, and the sine of the angle theta is going to be S2 over L. So if I rearrange this, S1 is equal to L cosine theta, and S2 is equal to L sine theta. So that means the area, let me call it area 1, is going to be T times S1, but that's T times L cosine theta. But T and L is the area of the blue plane, so I'm going to rewrite this as the area of the slanted plane times cosine theta. And in a similar way, area 2 is the thickness times S2. It's the thickness times L sine theta. It's the area of the slanted face times the sine of theta. Now that I have those areas, I'm going to multiply them by those particular stresses. So let me set up my force block, and I'll start it on this page where we have these areas defined, and then we'll do our equilibrium equations on the next page. Okay. So the force, I'll call that F in the n direction, is going to be sigma n times A a force in the t direction I'm going to call, let's see, what tau nt times a. And then I'm going to get a force in the x direction, the horizontal direction. I'll call it Vx. And that's going to be equal to the shearing stress on the bottom tau times the area on which it is acting. And in this case, that's area 2. That's a sine theta. And then a force in the vertical direction, I'll call Vy. It's going to be the shearing stress over here times the area of the inclined plane times the cosine of theta. Okay, so we have all those different forces acting on the block. So now I can apply my equilibrium equation. So we have a choice to make. We can either do the summation of forces in the x and in the y direction, or we do the summation of forces in the n and the t direction. Since what I want is an equation that has sigma n and tau nt, it would probably be easier than if I do it in the n and in the t directions. So that's what I'm going to do. Here's the angle theta as it's defined. So let's see, let's write down summation of forces in the n direction. I'm going to have sigma n times a, and then I'm going to have a component of both of these two forces in the n direction. So let's break this up into components. We're going to have to do a little bit of trigonometry, geometry, to figure out which one of these two is the angle theta in this force diagram. Let's see, let's draw a line down a little bit further. Let me draw the slant. The angle from the horizontal over this way is the angle theta, so that means this is the angle theta as well in this picture. All right, so if I do the summation of forces in the n direction, I'm going to take this force Vy, and I want the sine theta component, and that's in the positive n direction. So I'm going to have plus tau a cosine theta, and then I just said I want the sine theta component. Now over here on this picture, let's extend this horizontal line a little bit. I'm going to draw in here the vertical line and the slanted line. This is the angle theta. Okay, this angle is going to be 90 degrees minus theta, because these two are at right angles. And this dotted line and the solid blue line are at right angles. So that means this is the angle theta in this picture. So the component of the force in the n direction is in the positive n direction, and it's plus Vx, which is tau, a sine theta, and in this case it's the cosine theta component, equal to 0 for equilibrium. Let's go ahead and do the summation of forces in the t direction right now. We'll have tau in t times a. From the bottom triangle, notice that that's pointing in the negative t direction, so I'm going to have minus tau a sine theta. That's the force, and it's the sine theta component. In the plus t direction, I'm going to have the force tau a cosine theta, and in that case it's the cosine theta component. If you notice, the area of the inclined plane is common to all of these terms, so these terms drop out. And I can do a little bit of algebra to solve for sigma n and tau nt. So let's see, sigma n, if I move these to the other side, I'm going to have minus 2 tau, let's write it this way, sine theta cosine theta, and tau nt is going to be equal to, let's see, move this one over, so that's a plus tau sine squared theta, but then a minus tau cosine squared theta. Okay, so that's what it is. Now we are going to do just a little bit more work to get these in a little bit more standard form. We're going to use some trig substitutions to write down what sigma n and tau in t are in terms of 2 theta instead of theta. Right? Now, tau sine theta cosine theta is sine 2 theta, but we have the minus sign there. So I'm going to say this is minus tau sine 2 theta, and sine squared minus cosine squared, well, you probably see it written this way. Cosine of 2 theta is cosine squared minus sine squared, so sine squared minus cosine squared is equal to minus tau cosine 2 theta. Now, these are very specific formulas that only works for the special case of a bar and torsion. And the angle has to be defined just exactly as I have it in this figure. And I don't want you to memorize these formulas. I do want you to understand how we got them, because applying equilibrium concepts and stress times area is force, those are important concepts to remember. But I don't think you need to memorize those very specific equations. However, we do need to talk about these equations just a little bit. So that's why we get them, and that's why most books have them listed. But I really don't recommend that you memorize them. Lastly, the thing that we have to keep in mind as we apply these equations is what tau is. Tau is the shear stress from torsion. On the outside edge of the bar, it's torque times diameter over 2 divided by the polar moment of inertia. Sigma n and tau nt are the stresses off at any particular angle. Let's draw this wedge again with just the stresses on it. As this angle theta changes from 0 to 90 degrees, the values of the stresses on the inclined plane change. Well, that means if they change, we ought to be able to find a maximum value for sigma n and tau nt. Just like we saw there was a maximum value for normal stress and shearing stress on an inclined plane in a tension problem, we could find these maxima for an inclined plane in a torsion problem too. Let's take a look at these formulas. If we want, we can take the derivative and set it equal to 0 and find the angles, but we did that for the tension problem, so let's just look at the formulas themselves. Let's look at maximum normal stress, sigma n. Well, what makes a maximum is, for a sine, maximum sine value is 1, and that occurs at 90 degrees when the argument is plus or minus 90 degrees. Now, since this is 2 theta in here, what we have is the maximum is going to occur for sigma n at plus or minus 45 degrees. If I do plus 45 degrees, sine of 90 is 1, I get the value of minus tau. If I do sigma n at minus 45 degrees, I get the sine of minus 90 is minus 1. That gives me a plus tau value. So whatever number that is, maybe 100 megapascals, and this is minus 100, and this is plus 100 megapascals. And it does happen at 45 degrees. There's that 45 degree angle again. We'll see why that is in general later on in the semester when we talk about something called Moore's circle. Well, let's now think about the maximum shearing stress. Right. What makes this cosine 2 theta equal to 1? Well, 0 degrees or 90 degrees will drive the cosine to its extremes. If I take the angle 0 degrees, cosine of 0 is 1, I get the value of minus tau. Now remember, when we drew our block, we had the arrow going down on the right side. That's why it's a negative sign. And because stresses at right angles are equal, that's why it can also be 90 degrees. And so in this case I get the extreme values of either minus tau or tau. Right, so the maximum shearing stress occurs in a block that's aligned with the axis of the bar in torsion. And the stress state looks like this. If I put a torque on it like I had shown at the beginning. And the maximum normal stress occurs at a 45-degree angle to the axis of the bar in torsion. On this face, this would be the plus 45 direction. We have compression, and perpendicular to it we have the tension. Okay, so the angle theta can be measured off this way. So this would be plus 45 degrees. Down this way would be minus 45 degrees. I'm going to redraw those stress states on the next page, and we're going to talk about those in a material behavior in a little bit more detail. Alright, so I just redrew those two blocks showing my shearing stress state and my normal stress state maxima. And the value of this in magnitude is tau, and the value of this magnitude is also tau. This is at plus 45 degrees and minus 45 degrees. So the interesting thing is, as we sweep from 0 to 90 degrees for theta, we're going to get different values of both normal and shearing stress. At 45 degrees, the shearing stresses all vanish, and we have tension and compression at 90-degree angles. If we look at this block, it kind of makes sense. You see these two arrows, they're pushing away, they're pulling away from this particular corner. It's like it's putting the net resultant in compression on that plane. So that's why this is in compression here. And at the same time, these two corners in the upper left are both kind of pushing together and putting this side in tension. If we were to take a look at the strains that are calculated at these for these blocks, the first block would turn into kind of a diamond shape as it gets distorted. This nice angle here that used to be a nice right angle becomes different than 90 degrees. It becomes a little bit smaller in this case. And the change, I guess that one actually opens up. This one gets a little bit smaller. The change in angle from pi over 2 radians, or 90 degrees, is the shearing strain. So gamma would be equal to pi over 2 minus theta star. At these two, on these two angles right here, this new angle theta star is bigger than 90 degrees, so I have negative shearing strains. And these two, okay, let me use theta star, but let me put it in a different color to emphasize that they're smaller. At those two corners, we're going to have positive shearing strains. if we wanted to use Hooke's law, we can calculate the shearing strains by the formula gamma is equal to the shearing stress divided by the shear modulus G for our linear elastic isotropic material. Now the strains at a 45-degree angle in the material are going to be a little bit different. If you notice, these two sides are pushing in and this is getting elongated. So let's see if I can draw a rectangle that shows that. Okay, I'm exaggerating these things so we can visualize what's going on. But here's the stretched out sides that are aligned up here. Here's the pushed in sides that are perpendicular to that. And we get some strains that are compressive on these two sides and tensile on those two sides. Interestingly, if we think of this diagonal of this diamond, that's the same as this dimension right here. And the other diagonal of the diamond, maybe going this way, is the same as this dimension right here. Let's call this direction the x prime direction and that direction the y prime direction. We can actually compute the strains in the x prime and y prime directions based on knowing whether we have plus or minus taus on those faces. So epsilon x prime is going to be equal to sigma x prime over E minus nu sigma y prime over E, and sigma z is equal to 0. Notice that I'm using 3D Hooke's law here. I have to use 3D Hooke's law because I have more than one stress component, more than one extensional stress component. Alright, so if I factor out the minus sign in the tau, I have minus tau over E, and then I'd have, let's see, 1 plus nu right here. Epsilon y prime would be equal to sigma y prime over E minus nu sigma x prime over E. And if I factor out the tau over E, I would have left 1 plus nu. Now if I wanted to find a strain in the z direction, or the z prime direction, if I call it that, then I would have sigma z over E minus nu sigma x over E, sigma x prime over E minus nu sigma y prime over E. And you see this comes to be a plus term, this is a minus term. There is no strain in the z prime direction for pure torsion. Let me just make a note here. Note, I must use 3D Hooke's law. Okay, so some of the homework problems, they like you to calculate the strains or make a sketch of what the strain state would look like, and this is what they're talking about for that kind of problem. Now there are some important implications of these stresses occurring at different angles. And if we think about material behavior, one of the things that I try to emphasize in this course is that ductile materials tend to fail due to shearing stresses, and brittle materials tend to fail due to normal stresses. What that means is we can estimate the failure mode of the material if we know that it's in torsion. The failure surface for bar in torsion since the maximum shearing stresses occur at this angle, the failure surface will be straight up and down due to this cutting action of the shearing stress. There's probably some good pictures you can find on the internet of this, and I also have a video associated with the Mechanics Materials lab. The distribution doesn't quite look like that, but it's a radial distribution. I'm trying to show here that this surface will go clean straight up and down. There's a video associated with the lab AEM251 that I'm responsible for, and you can see the failure surface of a ductile steel bar in there. So as these two pieces twist, the maximum shearing stress goes here. So this would be a shear failure. Now the fact that the maximum normal stresses occur at a 45-degree angle, where it's compression on this side and it's tension on that side for the bar that's getting twisted this way, that means that this surface is going to open up on this side. The thing about this is that this surface wraps around this bar in a helical pattern at 45 degrees. And so sometimes what you can see is a very nice helical fracture pattern. I don't know if I can draw it very well, but it kind of goes on both sides of the bar. Something like that. If you have a chalkboard and you have a piece of chalk, you can take that piece of chalk and you put a torque on it. If you get it really in a nice state of torsion, then you can generate this failure surface. It's kind of interesting looking. Alright, so we talked about the shearing stress state at an angle. We got some equations. You should know how to use the equations, but don't memorize them. We spent some time using the equilibrium approach to come up with stresses on an inclined plane for bar and torsion. And then we talked about the strains, and we talked about material behavior for ductile and brittle materials.